Lecture 36, the central limit theorem. This is kind of one of the big punchlines of the course. All right, so recall that if x is normally distributed with mean mu and standard deviation sigma, then for samples of size n, x bar is normally distributed, also has a bell curve with the same mean, it's centered at the same place, but the standard deviation is smaller, sigma divided by the square root of n. And another way to say that, I say down here, is that so if x is normal, x normal implies that x bar is normal. And remember our notation where I said if we're talking about maybe more than one random variable, and we want to refer to, which really means like two different populations of data, right? It's a way to think about it. And we want to talk about the mean or the standard deviation of one versus the other. We'll put a little subscript on mean to indicate which random variable we're talking about. So the mean of x bar, which is the random variable that is the sample mean taken from all possible samples of size n, that random variable's mean is the same as the original x's, and the standard deviation for x bar is the original standard deviation divided by the square root of n. And so the point was that if you had to do any kind of a problem that involved probabilities of x bar, you want to convert to z-scores, so you can use the z-table, and you convert to z-scores by using the original mean, but the standard deviation, you use a new one where you got the old one divided by the square root of n. And that's what we were doing last couple lectures. Okay, well, big amazing fact here is what I have there in bold, the central limit theorem, or CLT. And you might want to pause me and read it. I'm going to just read it very quickly here. Let x be any random variable. So again, think of that as any population of data, right? With mean mu and standard deviation sigma. So I'm not talking about one that necessarily is normally distributed, that necessarily has the bell curve. Then for large enough sample size n, we can regard the mean x bar as being normal with mean mu and standard deviation sigma over the square root of n. So you get these same conclusions, but we don't have to start with this original assumption. We can get that x bar is normal and that the mean is the original mean and the new standard deviation for x bar is the old one divided by the square root of n. We get that automatically, even if the original data set is not normally distributed, as long as the sample that we're looking at is big enough, as long as we are considering samples of a big enough size. And that is really an amazing fact. And I say here, let me just go ahead and finish there. So how big does n have to be? Well, for perfection, really to be mathematically, theoretically correct, we actually need n to just shoot off to infinity. We need n to get bigger and bigger and bigger. The bigger n gets, the more true it is to say that x bar will be normally distributed regardless of what x is. But in practicality, usually n bigger than or equal to 30 is just fine. Okay, so if you have a sample size that's bigger than or equal to 30, then what you have is when you compute the mean, you are getting a value of a random variable that is so close to being normally distributed that we can just go ahead and say that it is. And the truth is, you don't have to go as big as 30 in a lot of cases. In a lot of cases, you just go 12 or 15, and you have a pretty good normal distribution on your sample mean with samples of size 12 or 15. For some really strangely messed up data sets, you might have to go bigger than 30, okay? But we're going to use as a rule of thumb that 30 works. It works pretty much in any circumstance that you run into in the real world. All right, so I have, here is our rule of thumb. Rule of thumb, trying not to spend too much time writing. if the original data set is normal mu sigma, so if it has the bell curve, and that's its mean and that's its standard deviation, then the sample mean is also normal mu sigma over square root of n, and that's regardless of how big or small n is. That's what we've been looking at. If the original data set is normal, then x bar will also be normal. And there's its mean and there's its standard deviation. Okay, and that's what we've already been doing. So part 2 of the rule of thumb, I'm run out of room, and I guess it's readable. Write a little bit bigger here, I guess. But if the original, I said data set, really we're talking about a population of data. If the original population is not normal, or more generally, we may not know if it's normal or not. In that case, it's still true that x bar is normal with mean mu and standard deviation sigma over the square root of n, as long as n is big enough. And like I said, bigger than or equal to 30 is what we need. If we don't have that, then we can't really make that assumption, and we can't usually go forward if we're working a problem. But if you think about what we're talking about doing here, you know how if you have a normally distributed random variable, you compute its z-score, and then you can find out probabilities regarding that normal random variable, because you can get the corresponding probabilities for the z-score, right? We've done problems like that over and over. So what we're talking about doing is, what is the context in which we can do that for x bar? If I know that x bar is normal with this mean and this standard deviation, that's all I need to compute z-scores and get probabilities and all that sort of thing, right? Okay, so even if the original population isn't normal, as long as n is big enough, I can do this, and then I can find z-scores or whatever I need to do, right? If the original population isn't normal and n is not big enough, then we could still pretend this is true, and we could find z-scores and look things up, but we couldn't really trust our answers very much, because this really wouldn't be necessarily a bell curve, which means when I got the z-score, it wouldn't really necessarily be the z random variable, and looking things up in tables would give us numbers that we couldn't really trust, right? On the other hand, if the original population is normal, doesn't matter the size of n. And we'll do some examples here in the next lecture, but I want to do one real quick. Okay, so let's see. So here's my example. Suppose we toss a fair die 50 times, keeping track of the number that comes up each time. What is the probability that the mean of those numbers will be greater than 4? Okay, so what I'm talking about doing is I'm talking about thinking of the random variable x being the number that comes up, right? So x equals, I'm tossing the die, I'm not going to write all that down, but x equals the number that comes up. Instead, let's think now of tossing it 50 times, so we get a sample size is n equal 50, right? And x bar is that sample mean, okay? And we are asking a question about the sample mean. We're asking what's the probability that the mean of those numbers will be greater than 4. Okay, well remember that x, let's see, I think I have enough room here. X, which is just the number that comes up, has this probability histogram. Histogram, I got room, I guess. It just looks like this, right? We have 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And it really goes across like that, and then You got all these bars, right? It's the uniform probability distribution. It's uniform histogram. Okay, very not normal, right? X does not have anything like a bell-shaped curve. It has just a flat, straight across histogram. 6 bars, they're all at height 1/6, and it's pretty boring. Okay, well, what we're talking about, well, okay, so recall, let's see. We saw this. This is from lecture, I think I said 18. Yeah, this is from lecture 18. And then in lecture 22, you found that mu sub x was 3.5, and that sigma sub x was the square root of 35 over 12. I think I got like 17.5 over 6, and I just doubled numerator and denominator and you get 35 over 12. Or I think I might have had 70 over 24. Anyway, it reduces to 35 over 12. The variance is 35 twelfths. Sigma is the square root. Okay, well, in order to answer that question, the question that we're being asked, we are being asked a question about the sample mean x, where the sample size n is 50. Since 50 is greater than 30, 50 greater than 30, so we can proceed. We can proceed, and we can use the central limit theorem. I want to emphasize, this is not a bell curve, but the central limit theorem is telling us that the sample mean is going to have a bell curve to it. And what will its mean be? Mu sub x bar will be mu sub x, which is 3.5. What will sigma x bar be? It will be sigma x over n. Over the square root of n. So it's the square root of 35 twelfths over the square root of 50, and that works out to be, let's see, 0.24, 15229, 15229, etc. Lots of digits we can put on that. All right, but anyway, if I were to draw, let's see, I'm about out of room here, but what would I be drawing now? I'd be drawing here at 3.5 a bell curve that has a small standard deviation, right? So I'm drawing, something that's going like this, right? This is x bar, okay? Anyway, it's got the bell curve, which means, hey, here's its mean right here. Where is it? Right there. And here's its standard deviation, so I can compute z-scores. Okay, so what do we want? We want the probability that x bar is greater than 4. Isn't that what we're being asked for? The probability that x bar is greater than 4. So I'm going to use my transformation, which says this is, and certainly by now you should pause me and finish it out, because we've done this kind of a problem. Okay, so if you have done that, you should come up with the following. I want x bar minus the mean, 3.5, divided by the standard deviation, which is this 0.2415 ... I, of course, in your calculator, I keep as many digits as I can. And I want the probability that's greater than 4 minus 3.5 over this same thing, 415 ... Okay, so we get the probability that becomes z is greater than, and that becomes about 2.070. I'm going off here. Okay, so let me do it here. Equals the probability that z is greater than 2.070, and that goes on. But I don't need to go any farther because I can only go out to the hundredths when I look things up. So of course I'll get 1 minus the probability that z is less than 2.07. I can only look up z-scores to the hundredths, right? And that becomes 1 minus 0.9808, I think, right? Is that right? 9808, I believe, 0.9808. And so it's gone off there again, but right here I think I get the final answer is 0.0192. All right, that is the probability. A little under 2% that if I toss the die 50 times and compute the mean, it's a little under 2% that it's going to actually be above 4, right? So, 4 is right there, and that area is what we just found, 0.0192, okay? We'll stop there.